Okay, you're welcome to ICH 113 of today for this week. I need to share my slides. If possible, we should be able to do 2 lectures today. Okay, so let me just share my slides. How many lectures have we had so far? I think so hold on a bit. I'll share my slide. Okay. Once more, you're welcome to ICH 413, Petroleum Refining Processes. This is our week 2. So we're looking at oil recovery from exploratory well. Oil recovery from exploratory well. What is an exploratory well? This is the well that it's somebody's distracting me. They're not coming in on time. It's a deep hole in the earth that a petroleum or natural gas company drills in the hope of locating a new source of fossil fuel. I think it's in this class we have talked about exploring for crude oil. So now after locating a prospect well, position where we know we can find crude oil, the next thing is to carry out the drilling and bring out the crude oil. It's the recovering of the crude oil. So an exploratory well represents a risk for the company drilling it. It's because it is not known before investing in the well. So not known how much oil or natural gas can be brought out of that particular well. So it's a risk. Even though that place has been identified, that there's a well there, out due to, after carrying out the explorations, seismic explorations, and so on, that place has been identified, but it's not really known how much oil is there, how much gas is there. So it's a risk. So the well may turn out to be a profitable new source of fossil fuel, or it may contain non-commercial quantities of fuel that are not worthy of extracting. In the latter case, if it is one that is not, sorry, if the well is a non-commercial quantities, then the only option is just to plug it and abandon it, because there's no need of going ahead and you cannot really get something. And that will mean a lot of losses in even trying to drill the well in the first place. So there are several methods. We have 3 main methods of oil recovery. We have primary recovery, we have secondary recovery, we have the tertiary recovery method. What we mean by recovery is bringing out the oil from the well to the surface and to the refinery. So we're looking at primary recovery now. The oil well is created by drilling a hole into the earth with oil rig. I believe some of you are familiar with some of these terms. So the steel pipe is placed in the hole. When the hole is drilled, it's a steel pipe, like a casing, that is placed deep down into the hole to provide structural integrity so that the sand will not be falling in to block the newly drilled well bore. So holes are then made in the base of the well. At the bottom, at the end of the well that is drilled, there are some holes that are made so as to enable the oil to pass into that bore that is made down to the down inside to the well. So finally, a collection by valves. This is like several valves connected together, and it looks like a tree, and so it is called Christmas tree. This is fitted onto the top of that steel casing we're talking of that is drilled and put inside to preserve the integrity of the well structure. So this collection of valves that looks like tree, and it's termed Christmas tree, is fitted on top of that steel pipe. And the valves regulating pressures and controlling flows. So those different valves that are connected like a tree, what they help to do is to regulate pressures and control the flow of the oil that is coming out. So if the underground pressure in the oil reservoir is sufficient, then this pressure will force the oil to the surface. If we have sufficient pressure, the oil will flow on its own to the surface and then to the tanks. Gaseous fuels, natural gas or water are usually present, which also supply the needed underground pressure. So it's actually the gas that is also associated with the petroleum, and then water is also there. Those are the things that help to build that pressure to force out the oil and bring it to the surface through that pipe. So in this situation, it is sufficient to place a complex arrangement of valves, what I mentioned to you before as Christmas tree, complex arrangement of valves. We place it on the well head to connect the well to a pipe network for storage and processing. So you place that Christmas tree on top of the pipe that is drilled inside the well. And so, of course, like I mentioned, you have to bore some holes down deep inside the well to enable the oil to come up. And then the pressure will force the oil up. And then when it gets up to those valves like tree, this is a network that moves the oil into the storage tank for processing. Usually for primary recovery method, it's about 20% of oil in that reservoir that can be extracted using this primary recovery method. Only 20% of whatever oil is present in that reservoir is extracted by this method. And then we have secondary recovery method. So this method is an enhanced recovery method that is needed because only a small fraction of the oil in the reservoir can be produced by primary means or primary method that we just described, that it's having pressure on its own that is forcing it out. So the rest 80% is still there inside the reservoir. So you need to still bring it out. So in this case, it's an enhancement method that is used to force the oil out. So, and this method must naturally also be both economic and effective. This secondary enhancement method has to be economical and effective. Otherwise, people will be making losses. And so if the method that is to be used there is not economical and effective, then there's no need of using it and then wasting the money. So no need of trying. So over the lifetime of the well, the pressure will fall. And at some point, there will be insufficient underground pressure to force the oil to the surface. That is for us to be able to achieve primary method of recovery. So the pressure falls, and then you have to build the pressure in one way or the other. And that's the essence of carrying out the secondary recovery. So if the secondary recovery method is economical, most often it's always economical. So the remaining oil in the well is extracted using secondary oil recovery method. And this method uses some techniques that will aid and help the oil and build pressure inside the well to help bring up the oil from the reservoir. So sometimes pumps can be used. Beam pumps, electrical submersible pump can be used also to bring the oil to the surface. This is a secondary recovery method, which needs to be enhanced. So other secondary recovery techniques to increase the pressure is by using water injection. You inject water into the hole that you have bored, or you can inject natural gas, and then it will help build the pressure. You can even inject carbon dioxide or some other gases into the reservoir, and it will help and build the pressure that will force the oil up. So together with the primary recovery, secondary recovery generally allow 25 to 35% of the oil that is in the reservoir to be recovered. So, and then some examples of secondary recovery methods are water flooding. I've mentioned that you can pump water into the well and it will build the pressure. So that example here is water flooding. It's a primary recovery technique. And then in this case, where the primary drive mechanism used to produce the oil is depleted. What I mean is that the primary pressure that was there is already depleted, so you now use water flooding. So the water is recovered from water table, where you have water on the surface of the earth at a particular level, the water table. You recover that into the reservoir, and then this will displace the oil. So the water will be down and the oil will be floating on the top of the well, on the top of the water. So because of limited amount of dissolved gas remaining in solution, pumps are used to bring the oil to the surface. So when you now flood the well with water, oil will be displaced and stay on top of the water surface, and then pump can also now be used to bring it out to the surface. And another example here is that of sand fracas. Sand fracas is used in this case, because sometimes maybe that the deposit where you have the oil is a bit tight. So sand fracas is used to force and open, push and let the tight situation give way a bit. So the treatment is done under high pressure for formation of fracture of that tight location where the oil is. So use sand fracas, use pressure, and form fracture. So this is in the form of sand stroke gel mixture. Pump it into that the base where you have the oil, pump it in, and that tight place will be fractured by the sand gel mixture under that pressure. So once the fracture is done, so the once the fracture is allowed to settle, once it is done, then trapping the sand, the well is produced with a significant increase in production. So the fracture is done, and then sand is trapped inside there. So it means there's an opening now, easy access for the oil to flow out. So the description is it's just like changing a single lane highway into a 6-lane highway. That's what happens. It allows freer movement of the oil. So now we have tertiary recovery method. Okay, sorry. We have tertiary recovery method. This is a method that is used to reduce the viscosity of the oil so as to increase the oil flow. So in this case, thermally enhanced oil recovery method are tertiary recovery techniques that heat the oil and make it easier to extract. Heat the oil, provide a form of heat to the oil well, and then the viscosity of the oil will be reduced, and then the viscosity of the oil will reduce, and then the oil will be able to flow out easily. So one example here is steam injection. So it's the most common form of thermally enhanced oil recovery method. It's often done with in different ways. One is cogeneration plant, using cogeneration plant. In this type of cogeneration plant, the gas turbine is used to generate electricity, and the waste heat is used to produce steam. And then this steam is then injected into the reservoir. This form of recovery is usually extensively to increase oil production. It's used as in a particular place that it's been really used in San Joaquin Valley. This was used, it's been used to produce oil in that particular place because the oil in that place is that of very high density, is very heavy, and so it has to be, the viscosity has to be reduced so as to be able to produce. And then in the US, in that location, San Joaquin Valley, 10% of oil from US is being extracted or recovered from there using this method, cogeneration plant. Another method under tertiary recovery is in situ burning. In situ burning, instead of steam, some of the oil itself is burnt to heat the surrounding oil. Occasionally, detergents are also used to decrease oil viscosity. And another method, the third method, is carbon dioxide flooding. Remember, I told you you can pump in carbon dioxide as well. All this, will help to build pressure. So tertiary recovery allows another 5 to 15% of oil in the reservoir to be recovered. So beginning from secondary oil recovery, when the secondary oil recovery is not enough to continue adequate production, then you have to proceed tertiary recovery method. And then to use this tertiary recovery method also depends on the cost of extraction method. And it also depends on the price of crude oil. So if the extraction method, if it is not economical to carry out the extraction method, then it's not worth it. So if it's economical, the extraction method on the tertiary method is carried out. And also if the crude oil price is high, it is also worth carrying it out. So when the prices are high, previously unprofitable wells are brought back into production. That is when the crude oil price is high. The wells that were not profitable initially, one can go back and produce and know that definitely still make money. So, and when the price is low, the crude oil price is low, then one will not go back into extracting from such wells that are not profitable. Okay. So another method is cyclic steam stimulation. Cyclic steam stimulation is also known as Huff and Puff method. And this one involves 3 stages: injection, soaking, and production. Steam injection, and then leaving it for some days. Inject the steam, and you don't extract immediately and leave it there. That is the soaking. And then after that, after some time, you go to extract it to bring it out. So can soak for just not more than a few days. So then oil is produced out of the same well. At first, the natural flow will happen on its own because after soaking, some pressure is built at the water. So initially, natural flow will happen, but then production will decrease as the oil cools down. So once production reaches economical determined level, the steps are repeated again. The steps, I mean, you soak again in steam and then keep for some days and then extract it. When it cools, it will not flow again. And so you just keep repeating. So the process can be quite effective, especially in the first few cycles that you have repeated. Though typically you can only recover approximately 20% of the original oil in place. 20% of the original oil in place. Compared to steam flooding, which has been reported to recover over 50% of original oil in place. It's quite common for wells to be produced in a cyclic steam manner for a few cycles before being put on a steam flooding regime with other wells. So that is it. And then the mechanism was this mechanism of steam cycling was accidentally recovered by Shell. And this happened in Venezuela. One of the wells packed up and then they just left it there. And then after some time, the steam injector blew out, and then oil started flowing out. And then they checked out what happened. And they saw, oh, the steam soaked the well, and then after some time, it just came out on its own. So they decided to start using that method, steam cycling. So another one is steam flooding. In a steam flood, sometimes known as steam drive, some wells are used as steam injection wells, while others are used for production, for oil production. You have some wells use it for steam injection and the others for oil production. So the first is to heat the oil to higher temperature and thereby decreases its viscosity so that it flows more easily. And then the second mechanism is the physical displacement, employing in a manner similar to water flooding. The steam flooding is, the second step is somehow similar to water flooding when the oil is meant to be pushed to the production well. So the pressure is built. Initially, 2 stages in steam flooding. First of all, this decreases the viscosity. The second one, the pressure pushes the oil out to the surface. So while more steam is needed for this method than the cyclic method, it's typically more effective at recovering larger portion of oil. A form of steam flooding that has become popular in the Alberta sands is steam-assisted gravity drainage. Steam-assisted gravity drainage. In this case, 2 horizontal wells are drilled, one few meters above the other, and then steam is injected into the upper one. Intent is to reduce the viscosity of the bitumen to the point where gravity will pull it down into the producing well. So another method of tertiary recovery is polymer flooding. So polymer can also be used. Soluble polymers can be added to water before it is injected into the reservoir. So mechanisms that improve recovery, efficiency, mobility controls, improves this mechanism that improves recovery, efficiency, mobility control improves volumetric sweep efficiency. So there are some limitations. High oil viscosity require higher polymer concentration. So if the oil is very heavy, you have to use more polymer concentration. The results are normally better if polymer flood is started before the water-oil ratio becomes excessively high. So you need a lot more polymer in this case to be able to achieve good recovery. And then clay also increase polymer adsorption. So if there's clay at that place, and then you use this method of polymer flooding, it will enhance the recovery better. So that is it with that particular lecture, and then we're going to another lecture now. So I will stop sharing this and then go to share another lecture now, lecture 3. So we'll continue with lecture 3. So I'll just make it a slide. Yeah. So lecture 3 is talking of crude oil classification. Crude oil classification. Over the decades, crude oil has been classified based on location, geographic region, where it is located. It's been classified according to where it's located. So that is really limiting the information about the crude oil, because the crude oil does not really depend the composition, and so it does not really depend on the location. So there are other factors also that determine whether crude oil is good or is better or something. So that's why it's also important to further classify crude oil based on other factors. And one of such factors is the density of the crude oil. Density of the raw petroleum is classified based on API gravity. I'll tell you what API gravity is in the next slide. So either based on API gravity or also based on other non-hydrocarbon components such as sulfur. You will see that classification soon, how it is done. And so in addition to the geographic condition, you have the density, classification based on density, and then classification based on other non-hydrocarbon components like sulfur. And then, so the end result of all the classification helps to determine the price of the petroleum, and it also helps to determine how much demand will be there for a particular crude oil, irrespective of where the location is. Just a combination will help to determine these factors. So API refers to American Petroleum Institute, a trade association that represents the oil and gas industry in the United States. So API is involved in developing standards, certifications, and best practices related to petroleum exploration, extraction, refining, and distribution. So we use API gravity in petroleum industry. API gravity is a measure of how heavy or how light petroleum liquids are. Then you compare them to water. It shows how heavy, it's a measure of how heavy or how light petroleum liquids are when you compare to water. And it's used to determine the density of crude oil or petroleum products. So in this case, API, the higher API gravity, the higher the API gravity, the lower the density. And the lower the API gravity, the higher the density of the oil. So lighter oil have higher API, whereas heavier oil have lower API. Okay, so in general, if the crude oil contains high levels of sulfur, petroleum is classified as sour. If the level of sulfur is low, it is termed as sweet. So this is another method of classification. Just talked of the API that classifies it as heavy oil or light oil based on density. And now we're talking of classifying based on non-hydrocarbon compound like sulfur here. If it is a lot of sulfur, it is sour petroleum. If it is less sulfur, it's sweet petroleum. So the raw petroleum is of high density. The petroleum classification is termed heavy. I've already said that. So, and the density of oil is determined by the length of the hydrocarbon chains. So, if it contains longer hydrocarbon chains, then the petroleum is denser. That means it is having low API. So if it contains higher portion of short chains, the petroleum is less dense. That means it has high API. So besides chain length, the ratio of carbon to hydrogen also helps to determine the density of a particular hydrocarbon. The greater the amount of hydrogen in relation to carbon, the lighter the hydrocarbon will be. The less dense oil will float on top of denser oil. So, and it's generally easier to pump. So the less dense oil will come out first when it is pumped. The heavier ones stay below. The hydrocarbons in crude oil can generally be divided into 4 categories. So we have the paraffins. The paraffins make up 15 to 60% of crude oil. And this is a hydrocarbon that is of 1 to 2 carbon to hydrogen ratio. It means it contains twice the amount of hydrogen as it contains carbon. So, and these are generally straight chain hydrocarbon, either straight or branched, but never cyclic. Cyclic is not paraffin. So paraffins are the desired contents in crude oil. And these are the ones that are most useful as fuels. The shorter the paraffins are, the lighter the crude is. So we have naphthenes. Naphthenes make up 30 to 60% of crude oil, and they still also have the carbon ratio of 1 to 2. But in this case, they are cyclic compounds, otherwise called cycloparaffins. They are higher in density than the equivalent paraffins, that is, than the straight or branch paraffins. They are more denser, and they also have higher viscosity than paraffins. We have another one, aromatics. They constitute from about 3 to 30% in crude oil. You have 3 to 30% of aromatics in crude oil. They are undesirable because when you burn them, they form a lot of soot, carbon. They are much less in hydrocarbon compared to paraffins, either the straight paraffins or cycloparaffins. The aromatics have much less hydrocarbon, much less hydrogen. And so they are more viscous. Often you find them either solid or semi-solid, when an equivalent paraffin will be a viscous liquid under the same conditions. So we also have asphaltics also. Asphalts, they make up 6% of the crude oil. They have hydrogen to carbon ratio 1 to 1. They're generally undesirable in crude. They are sticky And this their sticky nature makes them excellent for use as use in road construction. They're very useful in road construction because of their sticky nature. So when considering petroleum classification, it's important to consider the fact that overall classification will have an effect on the value. The overall classification will have effect on the value, not just the physical properties. Example is that you get petroleum from a geographical classification from one region in the world, and it may be expensive. It might have all the qualities you want, but because you're transporting it from one location to another, then it becomes more expensive. So that is why it's important to consider all the different forms of classification when you're trying to look at the value of the crude oil. In general, lighter crude commands higher price because it contains more hydrocarbon chains that are easily refined, can be easily refined to make gasoline. Of course, you know that most crude oil is used for gasoline and fuel, diesel fuel mainly. So the one that is more useful for fuel is a lighter one. So if you have the lighter petroleum, it's much easy to refine, and it's going to give you a high percentage of fuel. And so it's going to be in high demand. The lower the sulfur content also of the crude, the higher the price, because you're not going to struggle to put in too much in the refining. So for sweet crude, it is easier to refine. For sour crude, you have to do a lot to remove the sulfur before you go into refining. So it's a more tedious and expensive method. So sweet crude is in higher demand, and lighter crude also is in higher demand than others. So classification of petroleum also indicates the best use of a particular field of petroleum. One oil type is not necessarily better than the other because the different types are useful for different applications. So light crude oil is preferable for refining into gasoline because it produces far higher yield than the heavy one. So in similar fashion, sweet petroleum is often more desirable, I've already said that, because it will give less environmental impact, to form less harmful compounds, not going to emit harmful compounds, much harmful compounds into the environment. So it's more desirable. So these basic classifications of petroleum are further enhanced by full molecular description gained through a crude oil assay analysis. So you get more enhanced, more description from crude oil assay. So now we want to look at alternatives to petroleum. We still have time. We still have 10 minutes. Okay. We want to look at alternative to petroleum. And time passed 2008. Top 15 oil consuming nations use nearly 60 million barrels of oil per day. United States used 19 million of that. China used 7 million, almost 8 million of the 60 million we're talking of. The top oil producers in 2006, they measured by barrels produced per day were Saudi Arabia, Russia, and US, United States. These were the top oil producers in 2006. So now it is estimated that perhaps in 2006, the peak oil has been reached, or perhaps it's already been reached by 2020. Peak oil is a point when extraction of crude becomes increasingly more difficult and more costly. Talking of moving from primary to secondary to tertiary recovery. So the result is high energy costs for everything from home heating to transportation. And I believe we're all seeing this is happening even in our Nigeria and some other places. So roughly 90% of vehicles in the world, they run on oil-derived products. And this accounts for about 70% of all petroleum used. In the United States, petroleum constitutes 40% of the nation's total energy use, and most of them go into transportation. So as fuel costs continues to rise, infrastructure of modern society is being threatened. And so this is why there is need for alternatives to fossil fuels in general and petroleum in particular. So there's several reasons for seeking for alternatives, and these include limited supply of readily accessible reserves, national security, environmental impact, and profit. So as primary use of petroleum is for transportation, replacing its use in that setting has been the target for most investigations, talking of towards alternative to petroleum. So transportation industry accounts for 14% of greenhouse gas emissions, and is exceeded only by industrial processes and electrical generation that rely upon coal. The retrieval, processing, and distribution of fossil fuels account for another 11.3% of greenhouse gas emission. So there's need for alternative to petroleum, and these alternatives to petroleum include alcohol, solar, wind, hydrogen, and biofuels. So we have a table here that illustrates the energy densities of the common fuels that we have. So when energy is standardized by energy density, the amount of energy in a given volume is easier to compare. So energy density can be defined as the amount of energy that is stored in a given system or material per unit of volume or mass. So the table I'm going to show you is going to show the amount of energy density, the energy in volume, and also in mass. So these are the energy densities of different material. We have for gasoline, when you're looking at it in mass, a kilogram, you have 47.2 megajoules. You're looking for it in volume, as in liter, you have 34 megajoules. So these are the different energy densities for the different materials. We're talking of alternative to petroleum. So based on what we have here, one can, decide and know this is going to be more useful for me. So the amount of energy, talking of joule now, still explaining what will help you to decide which of the materials will be more useful for you as an alternative to petroleum. So joule is the amount of energy expended in applying a force of 1 Newton over a distance of 1 meter. So joule, an example is that amount of energy that you require to lift a simple small apple for 1 meter off the ground is 1 joule. To lift small apple 1 meter off the ground, you will use 1 joule. So for a car that accelerates from 0 to 100 kilometers per hour, a car that the weight is 1,000 kilogram, accelerating from 0 to 100 kilometers per hour has approximately 365 kilojoules. So, and that will require 10 mils of gasoline or 65 mils of hydrogen from the above table that I showed you. Of course, 1 kilojoule is 100 joules, 1,000 joules, megajoule, 1 million joules, and terajoule, 1 trillion joule. So you can use these to calculate and know how much of these materials you can use for an alternative fuel. Now we look at natural gas. Simply methane, and always associated with oil fields, or it can be found on its own deposit. So it's a product of cracking long chain hydrocarbons. Methane, of course, is just one single carbon atom with 4 hydrogen atoms. It's the simplest, smallest hydrocarbon and cannot, of course, it cannot be broken further. So reservoirs made only of natural gas have occurred in 1 or 2 ways. Either the natural gas leaks from another petroleum deposit. Remember I say natural gas is always associated with petroleum, crude oil. So it's either it leaks from one place, or all the hydrocarbons in the deposit have been converted to methane. Everything has been cracked down to the lowest hydrocarbon. So high temperatures and pressures are necessary for natural gas formation. Of course, the temperature, it will help to crack down longer chains and form gas. So a general rule of thumb is that the lower the pressure and temperature, the heavier the hydrocarbon will be. Natural gas is only found near the surface if it has escaped from a deeper well. Methane is also commonly produced by bacteria, making it rather unique among petroleum products. Bacteria that produce methane are known as methanogens. You can produce methane directly from organic material under anoxic condition, that is, under oxygen-free condition. That's why you can get methane gas from dump sites and so on. So these are the bacteria that cause methane production in landfills, these methanogens. Some natural gas may be formed this way during early stages of petroleum formation, but most is likely lost to the atmosphere if there's not enough solid layer of sediment to trap it under. So, brought the lectures today to an end, And I don't know if anybody has any question to ask. I think we're just right on time. So, say any question? Okay, so, and I have to, we have to leave the live